When we gaze upon Saturn, our eyes are drawn to its most famous feature. We see a glorious, seemingly continuous disk of light. These are the rings. They wrap around the planet like a halo. For centuries, they appeared as a solid, unbroken band through our telescopes. But as our vision improved, a new picture emerged. We saw that the rings were not solid at all. They were a collection of countless individual pieces. And more surprisingly, they were not uniform. The rings are etched with dark, empty lanes. These are the gaps. They slice through the bright material, creating a pattern of stunning complexity. What force could be powerful enough to carve such perfect voids in this massive structure? To understand how gaps form, we first need to know what the rings are. They are not solid hoops. If you could fly through them, you'd be in a blizzard of individual pieces. These particles are mostly made of water ice. Some are pure, glittering ice. Others are contaminated with rock and dust. That gives them different colors and brightness. Some particles are grains of dust, too tiny to see. Some are pebbles or small stones. A few are as big as cars or small houses. Together, they make the vast, flattened disk we call the rings. Each particle is an independent satellite, following its own orbit governed by gravity. Particles closer to Saturn must travel faster. An inner edge particle can circle in just a few hours. Outer edge particles move much slower. That speed difference is crucial. Particles constantly pass one another. The rings are perpetual motion, a cosmic highway with billions of travelers. The ring system spans about 175,000 miles across. Vertically, it's only about 30 feet thick, thinner than a sheet of paper relative to its size. That extreme thinness comes from countless collisions. Tilted orbits collide into the equatorial plane. Energy is lost and orbits average out. Over billions of years, the cloud flattened and collisions grind large pieces smaller. So we get a vast flat disk of trillions of icy particles, each orbiting at a speed set by distance. But these particles are acted on by more than Saturn's pull. The biggest external force is Saturn's moons, the artist's brush precisely sculpting bright bands and dark gaps. Gravity is the engine that drives the universe. In Saturn's rings, it operates with a musician's timing. The key to forming gaps is a phenomenon called orbital resonance. Let's break that down. An orbit is the path a particle takes around Saturn. A resonance happens when two orbiting bodies, a ring particle and a moon, have orbital periods that are a simple ratio. For example, a particle orbits twice for every orbit of the moon. That simple, predictable relationship sets up a powerful interaction. It means they repeatedly meet in the same part of their orbits. Think about it this way. A single push may not move a stuck car, but timed, repeated pushes build momentum. Orbital resonance works the same way. Every time the particle and the moon line up, the moon's gravity gives a little tug, at the same orbital point again and again. It's not random, it's rhythmic. Each tug adds a tiny bit of energy, like a well-timed push on a swing. Over long periods, those repeated tugs matter. A single tug is far too weak to notice, but repeated thousands of times over millions of years, the cumulative effect is dramatic. The energy kicks make the particle's orbit unstable. The orbit becomes more elliptical, dangerous in crowded rings. The particle is more likely to collide, or to have its orbit altered further. Eventually, it moves inward, or outward, or is ejected entirely. That process clears a specific orbital path. The resonance acts like a gravitational broom, sweeping particles away at a precise radius, creating a narrow, well-defined gap. One of the most prominent and famous features in Saturn's rings is a wide, dark gap known as the Cassini Division, first observed by Giovanni Cassini in 1675. This massive gap separates the two brightest rings, A ring and B ring. It is nearly 3,000 miles wide, a vast expanse of near emptiness. For a long time, its origin was a profound mystery. Why would such a large region be so devoid of material? The answer lies millions of miles away, in the orbit of Mimas. Mimas is the celestial culprit, orbiting well outside the rings. Its gravity creates a 2-to-1 orbital resonance right at the Cassini Division. Any particle there circles Saturn twice in the time Mimas circles once. Every 2 trips, the particle lines up with Mimas and receives a gravitational tug. That repeated tug makes the orbit unstable, stretching it more elliptical. Collisions can rob energy, dropping particles inward, or add energy, flinging them outward. Over eons, this clears out the 2-to-1 resonance zone, leaving the Cassini Division. When you look at the Cassini Division, you see cause and effect on a planetary scale. The cause: Mimas's relentless, timed gravitational pull. The effect: a 3,000-mile wide gap. The division isn't perfectly empty. Cassini found faint, dusty ringlets, but it's dramatically less dense than the bright A and B rings. While powerful resonances carve wide gaps, they don't explain all features. Some rings are incredibly narrow with strikingly sharp edges, like the slender, kinky F ring. Left to itself, a narrow ring should spread and dissipate due to collisions. So, what keeps it so well-defined? Tiny moons orbiting very close to the ring. Shepherd moons. Like sheepdogs guiding a flock, their gravity herds ring particles, confining them to a narrow path. A shepherd moon orbits just inside or just outside a ring's edge, directly influencing nearby particles. An outer shepherd moves slightly slower. Its pull slows edge particles, making them fall to a lower, faster orbit, back into the ring. An inner shepherd moves faster. As it overtakes particles, it pulls them forward, boosting them to a higher, slower orbit, back toward the ring. With 2 shepherds, one on each side, the ring is trapped between them. The F ring is bracketed by Prometheus and Pandora, potato-shaped moons patrolling its edges. Prometheus sometimes passes close, pulling a streamer and carving temporary channels that shear as it moves away. These interactions leave dark channels, bright clumps, and strands, later smoothed by subsequent passes. Pandora helps stabilize, yet adds to the ring's chaotic appearance. Shepherds also maintain sharp edges, Atlas outside the A-ring as primary shepherd. Pan within the Enki gap, acting like a gravitational snowplow. Pan keeps the gap open and creates boat-wake ripples, a visible signature of its gravitational reach. In the end, the story of Saturn's rings and their gaps is a story of gravity, time, and motion. The rings are not a static monument. They are a dynamic, constantly reshaping celestial sculpture. The primary artists are the moons. Through orbital resonance, distant moons like Mimas clear wide lanes like the Cassini Division. Their rhythmic pulls create zones of instability, eject particles, and carve voids in icy sheets, shaping the large-scale architecture. Meanwhile, tiny shepherds work the fine detail, preventing spread, policing edges, creating waves, braids, and streamers. Resonance and shepherding together produce the structure we see. Gaps are not imperfections. They're essential negative space defining the rings. Every gap, edge, and ripple is a clue. By studying them, we learn about Saturn and how planetary systems form and evolve. The rings remind us the universe is a place of constant change under physical laws. Seeing these precisely carved gaps fills us with wonder, a testament to gravity's patient, creative power. The gaps exist because quiet, persistent moon gravity shapes the dance of ice particles.